We have the pleasure of having Dr. George Veni. He is an internationally recognized hydrogeologist specializing in caves and karst terrains. He's the owner and principal investigator of George Veni and Associates, conducting multidisciplinary environmental karst management research throughout the United States and in several other countries since 1987. In 2007, he serves as the executive director of the National Cave and Karst Research Institute until 2023. He has chaired 19 international karst conferences from 2002 to 2022. He was a member of the governing board of the International Union of Speleology, serving as president for the final 5 years, and was the organizer of the International Year of Caves and Karst in 2021/22. He's been a doctoral committee advisor for geological, geographical, and biological dissertations at 5 universities in the US and Greece. 3 cave-dwelling species have been named in his honor, and he has published and presented over 290 pages, including 6 books on hydrology, biology, and environmental management in karst terrains. So with that, I present to George Veni. You might be you're muted, George. You're muted, George.
Okay, got it. I thought Don would unmute me, but no problem. So let me switch over to the screen. There we go, and get started here. And first of all, I'll thank everyone for the invitation to come and meet with you today. And there we go. Caves and karst. These are features that are just incredibly common in our world, and yet most people know little about them. I believe that everyone in the world is touched to some degree, directly or indirectly, by caves and karst. And the purpose of this talk is, as it says, it's an introduction to make people better aware of them. And I developed this presentation while I was the executive director of the National Cave and Karst Research Institute. So I'm still using their format as I set it up when I created this presentation. But let's start with the word karst, because that's something that most people simply aren't familiar with. I'll define it in a moment, but first I wanted to show you the distribution of karst worldwide, and it's shown in blue on this map here. Karst areas cover about 20% of the land surface of the world. It covers 25% of the land surface of the US, including a terrain that we call pseudokarst that's related, and I won't get into that. And it's even more widespread than that. When we developed this map in 2017, we only mapped the areas where karst was exposed at the surface, but there are many parts of the world where karst processes occur in the subsurface. They don't appear at the surface. In the US, I estimate that maybe 40 to 50% of the US is underlain by some sort of karst, even if it's not exposed at the surface, affecting various things that we do and how we live and our economies and so forth. So we can potentially expand that globally to expand the 20% number globally to maybe 40, 50%. It's hard to say. It's really hard to map what's in the subsurface. But technology is improving and we're getting there. So what is karst? It's a type of landscape. It's a terrain. And unlike most landscapes formed by water flowing down valleys, flowing over the surface and mechanically breaking up, eroding the rock, in a karst area, we're talking about dissolution, dissolving away the bedrock. And so it's primarily a chemical process that happens slowly over millennia. Typically karst forms in limestone, dolomite, and marble rocks. And in arid terrains, gypsum and super arid terrains, halite, rock salt. Typical features we find in karst are caves, sinkholes, underground streams, and those underground streams feed the world's largest springs. So this photo here from China, where I'm standing, there's a cave entrance. It's about 150 meters tall, almost 500, about 500 feet tall below me. And this underground stream, this river flows down into it. And what you're seeing here is a collapsed portion of the cave. There's a natural bridge that hasn't collapsed in yet. And it's draining this karst area. As we look at the mountains in the background, we see these peaks, and we tend to think, wow, did they get pushed up individually? But no, what happened was the whole area was uplifted, and then water moved down through fractures, dissolving away the rock and leaving these individual peaks behind, eventually coalescing in the subsurface to form an underground stream. So this is quite a dramatic karst area. And I'll give you other examples as we go further on. But I'm going to focus the first part just to explain what karst is, how karst works, and how caves are involved. And part of that is to describe an aquifer. Um, an aquifer, by definition, is an underground reservoir of water, and it must be economically accessible for human use. No one's going to spend tens of thousands of dollars drilling a deep hole to get a teaspoon of water. So it needs to be economically accessible, a significant amount of water. Now, the word reservoir kind of throws people off because people will see this and think, oh, reservoir, you're talking about underground lakes and rivers and streams and such. And no, not really in most cases, in many cases. So here are three types of aquifers, general classifications. And in each of these diagrams, the scale changes dramatically. So here on the left, a porous meaty aquifer, we're looking at a microscopic scale. We're looking at, let's say, a sandstone aquifer. And so we're looking at grains of sand here, and water moves through and around these grains of sand or gravel, silt, whatever, these tiny particles might be made of. Water flow is fairly uniform. You can predict where it's going to go, how fast it's going to get there, and it's a great filter for contaminants. And so this is a porous meaty aquifer. And in fact, most studies, most hydrogeologic textbooks focus on porous media aquifers. Now, fracture aquifers, you're looking at these cracks in the ground. This usually occurs in like a granite, a crystalline type rock. And the scale here is life size for what you may be seeing. These cracks may be a bit larger or smaller than what you're seeing on the screen. But in this case, the water flows through the fractures, and the degree of movement, the rate of movement, the direction is dominated by the fractures. So you can somewhat predict how the water is going to go, where it's going to go. But it is certainly a bit more of a complicated system than porous media. Now, karst aquifers, the scale here can be variable. It can be as large as you see on your screen. It can be smaller. These holes that you see here can be large enough to fly an airplane down. So we're talking about a very different system. And water can flow in very different directions, flowing out here, there, coming in here. These are simply the most complex aquifers in the world, and we'll talk more about that shortly. So how do karst aquifers form? Water moves down through the ground, and it moves down through fractures. And because the limestone itself, and I'll primarily stick with limestone as the most common type of rock where karst aquifers form, but the rock is dense, and while water does appear within the microscopic matrix of the rock, it moves more easily through the fractures. And so as these fractures, as water moves through these fractures, the water will begin to dissolve the rock into what we call a conduit. Now, a conduit is anything larger in diameter than your pinky finger. And so this is a larger conduit, but anything larger than your pinky finger hydrologically functions the same way. When it's smaller, there's filtration and other factors that occur. But what happens is as conduits get larger, they're more efficient to transmit water. And so the water now, instead of going straight down and fighting its way along fractures, will move horizontally along bedding, along these partings in the rock to the conduit so it can flow more easily. Water is going to find the easiest way to flow. And because more water is now flowing through the conduit, it's going to increase it's going to enlarge at an ever increasing rate. And when it becomes large enough for a person to enter, we call the conduit a cave. So caves are simply humanly enterable conduits. So again, a hole the size of your pinky finger hydrologically functions the same way as a cave does. So how do karst aquifers work overall? The basic hydrologic cycle starts with clouds in the sky dropping rain on the ground. Some will move into the matrix of the rock where it might sit there for thousands and thousands of years. Some will move into fractures and slowly move on through. Some of that water may drip into caves and form stalactites, stalagmites that you'll see if you go to any show cave in your area. Um, some of the fractures will enlarge to the point that they'll form these funnel-shaped depressions that we call sinkholes, and these are formed to transmit water down underground. Other sinkholes may form by collapse, where there's a pre-existing cavity down below, and the roof just gets thin and weak and it falls in. But basically, water is trying to move vertically down through the system to this dotted line, which is the water table. Below the water table, every crack, crevice, conduit, cave is filled with water. So once the water reaches the water table, it's going to begin to flow horizontally to where it can drain out of a spring. In some areas, the water may move deeper and go deep below some confining unit where the water can't move up through this impermeable rock, but they'll find a fracture where it can eventually try to drain up and reach the water table. And of course, it doesn't shoot into the sky. It just, with the weight of water, just causes to flow downward down the valley. Now, these are complex systems, not just because of the different permeabilities, like I say, within the matrix. Permeability refers to how easily water can move through a substance. But when people talk about how old is the water in a karst aquifer, is it thousands of years old, hundreds of years old, days or hours old? The answer is yes. It's all of the above. It just depends what part of the system you're sampling. And so the chemistry, the hydrology, varies dramatically depending on what part of the system you're involved. But additionally, we have this other factor of time, that the aquifer evolves over time. So in the past, water flowed horizontally to the valley through this passage, but then the valley cut deeper and now water's flowing down through here and coming out through here. And as the valley continues to cut deeper, water in this current water table area will be drained and will flow out through here. And yet, under the current situation, you can have floods in your aquifer and water can rise up and go out to reactivate these dry passages. And while in this simplistic sketch, you see it would flow back into the same valley. That doesn't always happen. It may go into a different valley, to a different spring, to somebody else's well who thought they may not have been affected by whatever's going on in this area. So these are incredibly, incredibly complex systems. So with that, just to give you the basic background, let's visit what karst landscapes look like. And they range from dramatic to hidden. And we'll start with a couple of examples of visually dramatic landscapes. And these two are from China. This is what we call tower karst, and this is what's called pinnacle karst. Some of the towers are up to 100 meters high. Some of the pinnacles are like 20 meters high. And somewhere here, I thought, no, no, it's not in this photo. It's a different photo. But anyway, these form typically where the rock is massive to thickly bedded. And what that means is most sedimentary rocks like limestone form in beds, form in layers. And so here you can see a layer. You can, there's another, horizontal parting here in the rock showing the different layers. The stuff here doesn't have layers, it's just massive. It also occurs in areas with moderate to high rainfall and in areas of regional rapid uplift of the land. And so we tend to see the most dramatic karst in the world in China and Southeast Asia because the Indian subcontinent drifted through the Indian Ocean and slammed into Asia, creating the Himalayas, and that people are aware of the Himalayas, but they often don't realize that much of the plateau in southeastern China, Southeast Asia was raised by that impact rapidly. And so water did its thing. You had good amount of water raining on down, dissolving open fractures vertically downward to create these pinnacles, to create these towers. And if you ever get to China, go to Guilin and go on the Li River tour. It's just spectacular, just spectacular. Another form of dramatic landscape is what we might call cone karst or cockpit karst. So here closer to home in Puerto Rico, some of you may be familiar with the Arecibo radio telescope that unfortunately, I believe it was this tower that recently collapsed and destroyed it. But the radio telescope is seated in a large sinkhole. That's and actually the Chinese now have built an even larger one. This one's about 300 meters in diameter. The one in China is 500 meters. And they were looking for a nice natural bowl-shaped structure to hold the thing and support the thing. And so what you're looking at is all these hills are, think of like egg crate where you nest your egg in. And in between each of these hills is where you put the egg, giant sinkholes, in this case, about 100 meters in diameter. In other cases, the chocolate hills in the Philippines, all that's left are the hills and the flat plain around them. So these are some of the more dramatic examples of karst. Now, more typical or what we'll call classical karst landscapes are somewhat karst hidden in plain sight. Unless you look closely, you may not really notice that this is karst, that there's something different about it. So we'll start up here in the region that's actually known as the classical karst, where the word karst came from. It is from the region known as the Kras, which the Germans took and made it into karst, good German pronunciation for the word. And you look at this field, but this field is actually a giant sinkhole. And periodically, annually, actually, it floods, and it's a great place to grow your crops and their agriculturally productive areas. And so these hills have lots of smaller sinkholes and caves scattered around them. If we come here to central Kentucky, right near Mammoth Cave, we've got this broad sinkhole plain. If you take Interstate 65 from Louisville down to Nashville, you'll drive right through it, and you'll see sinkholes off to the side. Some of them hidden by trees. Some of them will, in this case here, is actually what we call a sinking stream, a stream coming off and then just sinking right down in there. So it's a bit more gentle, more subdued landscape. The rock isn't as thickly bedded, but still moderate rainfall. Uplift is low to moderate in those areas. Then we have subdued karst, which may not be noticed at all. So on the right here in central Texas, this is from San Antonio, where I've lived and worked for many years. Here's a sinkhole that's about a meter long, half meter wide, a few centimeters deep. You just don't even think it would be anything. You could casually walk by it and not even notice it. Now, here's where I live now in New Mexico, just up the road from Carlsbad Caverns National Park. You look at this and you say, well, it's just some desert mountains. You don't see anything that would tell you that this is karst, unless you happen to stumble across Carlsbad Caverns, and there's a big hole in the ground here. In each case, you've got water moving through this landscape easily through highly permeable fractures dissolved away by karstic processes. Digging open this hole here north of San Antonio would almost certainly lead into a cave. That's important for the aquifer that these people depend on. And here in Carlsbad, the city of Carlsbad, we depend as our only water supply on the water that goes into the rocks here at Carlsbad Caverns National Park and associated areas, and then drains off in our direction. Now, hidden karst, being a little bit loose here with terminology, but really we're talking about caves. Again, focusing on underground streams. Here's a cave in Italy, Grotte Falvatera. For scale, here's a couple of people at this cave in Lebanon, which captured a surface stream, so it now flows underground. Trying to manage and deal with karst can be difficult. The U.S. Environmental Protection Agency developed something called DRASTIC, and DRASTIC was an acronym, and each of the letters stood for something that you would tally the points, and it would tell you how sensitive an area was to contamination. Well, the D stands for depth, and in this case, depth is meaningless because the idea was the deeper it was from the surface down to your aquifer, the deeper it was, the safer you were from contamination. Well, in karst, here we see water plunging, free falling 80 meters right down to the water table. So depth is meaningless. So this starts to give you a hint of some of the sensitivities and issues that we have in dealing with cave and karst areas. So let's delve into that a little bit more. Again, karst aquifers are the world's most complex groundwater system. Here's a block diagram developed by the Missouri Department of Natural Resources. And just as an example of some of the sensitivity, here's a home on the landscape. They have a septic system. Now, the way the septic system should work is that effluent is released into the soils. They're thick enough, water moves through them slowly enough that the contaminants, and we're primarily talking about bacterial contaminants, they break down, they're absorbed by the soil, and then the water that works its way down into the aquifer is clean. So, and not really an issue. But in karst areas, it doesn't always work that way. Because see, right here, you have a sinkhole, and maybe there's no expression of it at the surface, maybe just a little bit of a dip in the soil, but maybe not. But because you have this sinkhole filled with soil, you've got water that's going to be channelized, and water will rapidly move down into this buried, filled sinkhole, get into the conduit system, move on down, potentially come back up into the water well to contaminate it. Some may jump over and go over this way to a spring. During high level water levels, as I mentioned, during floods, it might jump over and take a completely different route. So again, this just gives you an example of some of the issues we have. Unfortunately, also, many sinkholes have been used as trash dumps. In rural communities, they often don't have good collection systems, community collection systems to dispose of trash, and so historically, a lot of trash has just been dumped in the hole and into the back pasture, and causing problems. Karst aquifers are the easiest to pollute. This is in central Kentucky under the city of Bowling Green, Lost River Cave. We've got this upper passage and the water spilling on down here to this lower passage. The black stuff you see here, we've scraped away some, so there's some of the rock behind it. The black stuff you see is oils, grease, sewage. We sampled this, and it was in excess of safe drinking water standards for 14 carcinogenic chemicals. This meter here was telling us about air quality and whether it was safe to go ahead or if we need to leave the cave and go get the spacesuits to continue the exploration and study of the cave. So incredibly easy systems to pollute. Again, incredibly complex, incredibly easy systems. There's effectively no filtration that occurs in karst. The fact that my friend and I were in this cave and we didn't get filtered. Think about it. In a sense, we're giant contaminants. So how can smaller things like bacteria, oil, grease, other chemicals get filtered? And so effectively, again, there's really no filtration effectively that occurs in karst areas. Now, karst aquifers are also the easiest to deplete. So imagine you're drilling a well for water and you're up into this cave, and this is a show cave. Obviously, you can go for great boat rides and go far ways up into this cave. But imagine you drill into this cave and you're into this underground stream. Well, great. You just figure, I've got all the water I need. You can put as big a pump as you want there and just keep pulling that water out. And that's what happens in many karst areas. Um, Maybe though they don't have hit a cave quite this large, but they get a lot of water and they don't realize, they don't think that just because I can pump water out at a certain rate, it doesn't mean that the aquifer is going to be replenished at that rate. And so just down the road from me in Texas, for example, there's some springs in the city of Fort Stockton that went dry long ago. They were the jewel of the community, the whole reason that community was there. They went dry in the 1960s because some big wells were put in that drained much of the aquifer, and those springs no longer flow. So that's a real concern also with karst. It's important to also recognize that I'm not talking about isolated instances. Karst aquifers are the primary or sole water supply for about 700 million people around the planet. That's about 10% of the Earth's population. So we're not talking about isolated instances. Again, we're saying that 20% of the land surface worldwide is karst, and perhaps much more than that in terms of where karst may be buried, and karst aquifers may be under non-karstic rocks that aren't included in that mapping, but still provide water to many communities. So there are challenges, land use challenges in dealing with karst, and the most common one that people are aware of, I don't have time to go into all of them, but is sinkhole collapse. In the US, sinkholes became really well known. They hit the radar in May of 1981 with the Winter Park sinkhole in Florida. It's about 100 meters in diameter, swallowed a swimming pool, a business, a couple of Porsches. And it was pretty exciting and made the headlines and raised people awareness of sinkholes. In 2015, a friend of mine with the U.S. Geological Survey did a study to find out how much damage occurs in the U.S. from sinkholes. And there simply isn't a whole lot of data out there. So he had to limit his study to only road damage. Not all states record damage and repair relating to sinkholes. Some will just say we spent X amount of money this year to repair roads, whether it was just gotten old and worn out or whether it was due to a sinkhole. But others do record it. So he came up with a figure, $300 million a year, and that's a minimum number spent in the US to repair road damages from sinkholes. Some make the news. This one here, also in Bowling Green, Kentucky, you can see the asphalt that collapsed down. Sewer lines intercepted here, under the road. Anyway, some of these make the news. Most don't. Most they're scattered over time and space. Because the news isn't going to report about some little hole that it cost the county $5,000 to fix. They're going to, the big ones that swallow cars and people, and this one swallowed 5 cars, and fortunately, no one was hurt. And fortunately, also, and this is an example of some of the problems that occur because many people don't understand karst. or don't believe things. My old master's thesis advisor told the city not to build the road in this area, um, and they did it anyway, and it collapsed. But fortunately, the engineers paid attention to them, and you see this yellow line here. Uh, that's a natural gas line. And the engineers knew that there was a potential for collapse, so they made they put the natural gas through this flexible pipe that actually bent under all the collapse and came up intact on the other side and didn't break. Because if that broke with the 5 cars trapped in here, all the sparks flying, boy, they would have proven the Big Bang Theory. And so quite lucky in that regard. But anyway, this is a minimal figure, only road damage. It doesn't include the loss of property, such as here at the Winter Park sinkhole. Doesn't include the loss of lives, and lives have been lost. Let's switch topics now to life underground. If you have space, life is going to occupy it. And so there are different types of cave animals. And this is my little sweetheart here, Cueva, Spanish for cave, because I found her in a cave, nearly dead of starvation. She went in there for shelter. She was lost, and she didn't belong in there. She's not equipped to survive in a cave. And so accidentals will either go in there temporarily and then go out and do their thing, or if they're injured, they may just die in there and never come out. Troglodytes are the first level of adaptation to living in a cave. These are animals like these crickets that will spend a significant part of their life cycle underground, but they must return to the surface to complete some necessary part of their life cycle. Typically, it's feeding, sometimes it's mating. In the case of crickets, they're going to go out to feed each night. The next level of adaptation are troglophiles. These are animals that could spend their entire life cycle underground, but they could make it on the surface too. So they have a higher degree of adaptation. Now, one thing all of these three have in common are eyes. You can see the eye there and the eyes here. As we move to the next and ultimate stage of adaptation, we have troglobites and stigobites. These are obligate cave dwellers. They must complete their entire life cycles underground. They cannot survive on the surface. The difference is between the two is that these live in air-filled conditions and these are aquatic. And so there are no eyes, no eyes. They, as the species, as animals get more evolved, they tend to develop elongated appendages. So this millipede here has fairly long legs. For millipedes, the same thing for these little amphipods. They become often depigmented. And the reason for these adaptations are that a cave environment is a food-poor environment. You're mostly dealing with decomposing organic material. You don't have the sun as your primary source of energy. And so evolution gets rid of things you don't need. Pigment is to protect you from the sun. Why produce pigment when you don't need it? Eyes, well, you're in a dark environment. Evolution gets rid of them. Why produce eyes when you don't need them? And elongated appendages, because it takes less energy to move through a dark environment if your appendages are longer. So anyway, these are biologically, ecologically fascinating environments that occur underground. Now, when most people think of caves, though, and cave life, they think of bats. And this shows part of the bat flight from Bracken Cave. Bracken has the world's largest bat population. That's averages around 16 to 20 million bats that live in there. And bats alone, there's an organization based in Austin, Texas called Bat Conservation International. They have determined that over 450 foods, industrial products, and medicines are directly or indirectly the result of bats or their activities. So these are incredibly useful, incredibly beneficial animals. Now, pest control is something that some people don't think about, with bats. This again is Bracken Cave, but this is the radar system, Doppler radar. The city of San Antonio is right here. And this cloud that you see is the beginning of the emergence of bats from Bracken. And you can see the emergence from other caves, in the area as well. The bats from Bracken, on average, they eat about 500,000 pounds of insects each night. 500,000 pounds of insects each night. So about 8 years ago, I think it was, there was a study that was published in Science, the journal Science, and they found that on average in the United States, bats save American agriculture $23 billion from the cost of chemical pesticides, because bats are controlling these agricultural pests, that affect corn, that affect cotton, that affects, so many pecans, so many other things. $23 billion. And that doesn't even include the health benefits of not having those chemicals in our environment. So tremendous benefit that we get from bats. Now, if we really zoom in to the tiny levels, I've talked about caves as a geologic process, but we now understand that there are microbial processes as well. And so here we see some microbes that are just loosely called, beads on the string or pearls on the string. We're finding that these microbes are important to help create caves, but also what's happening is we're finding unique microbes in the underground environment that have shown great promise for, again, perhaps not food, but certainly industrial products and certainly some medicines. So there's a lot of benefits that we're looking at from cave ecosystems. Let's switch now to cultures, caves, karst, and cultures. Uh, Prehistoric cave life. The myth is this: that people would go into caves. They're great. That's where the proverbial caveman lived, and so that's where our predecessors hung out. Not really. I mean, this is a fabulous cave in Cuba. Um, and look at it. You've got water. It's a moist environment. You've got a nice cool breeze coming through the cave. You don't want to live in a breezy, drippy, wet environment that might flood periodically. That's just not how, most people want to spend their time. The reality is that most people who lived in caves lived in shelter caves, just little shallow caves that don't go very far back into the bedrock. They're dry. The fact that there's a back wall means that there's no breeze coming through it, but it also allows better climate control. So you could put up a little screen made of animal skins in front of it, start a fire, and it would keep you nice and toasty warm inside. So, or take down the screen in the summer and enjoy the shade and not be in the summer heat. So people living in caves were mostly in rock shelters as opposed to deep inside caves. Instead, the deep cave use was either for art or ritual, primarily. So here we see on the left from Chauvet Cave in France. These paintings are 35,000 years old, preserved in these caves, in this particular cave that's now dry, hydrologically inactive. Amazing stuff that's there. There may have been ritual associated with some of this art. We know that with some cave art there was ritual associated. In some, it's not clear. In some cases, caves may have been used for more practical purposes. But here on the right, this cave known as Balamku in Mexico, in the Yucatan, you see these incense burners, these incensarios. You can see a face on this one over here. Someone didn't just walk into a cave and drop these here. They had to crawl long distances and not break these big, heavy vessels. And they were conducting rituals deep inside this cave. So caves had their purposes other than just living. They were again primarily for art and ritual. And because once a cave is hydrologically inactive, it's a time capsule. It preserves material for thousands, hundreds of thousands, of years potentially, depending on how long the cave itself will survive. And we'll get back to that in a moment. Let's look at some of the modern use um, of caves, from resources to sacred geography. Um, in West Virginia and other states during the Civil War, during the Revolutionary War, um, caves were mined for their sediments because they were high in nitrates and they would be used to create saltpeter that was used in gunpowder. In Japan, as well as other places. Took this photo at Narusawa Icicle Lava Cave, where ice naturally forms in this cave. And people would go in and carve out blocks of ice, wrap them up, and then deliver them to the emperor, to the elites. And then back to the Maya area. This is in Belize. Um, Sacred geography. Caves have been sacred to many cultures. And I would say probably, at least to my knowledge, to none more than the Maya of Mesoamerica. And part of the reason was that 70% of the Maya area was karst. And so if you wanted water, you had to go underground to get it. You had to walk into caves. And so they had their practical uses of water. But additionally, there are some very large caves and sinkholes in this region. And when warm, humid air is drawn into these cooler caves, it condenses and forms clouds. And so the Maya believed that not only could you go into caves for water, for life-giving water, but caves and sinkholes would give birth to the water, to the clouds in the sky, which caused the rain to fall in the fields, which can perpetuate the whole cycle of life. So as a result, caves were critical to the Maya. And where they built their temples, where they built their communities, it was often dictated by caves and related features. Now, as I said, caves can preserve material, and there's growing recognition by people who study climates, past climates, that caves are the richest sources of paleoclimatic and paleoenvironmental information. There's incredible work that's been done to study past climates by drilling deep cores into the ice in Antarctica, drilling deep sea cores out in the oceans. And that tells you what's happening specifically at the poles and in the middle of the oceans. It's not telling what's happening in your backyard, but you extrapolate, you interpolate from there. But caves are in our backyards. If we study the 1,000 caves in each continent, we could develop this detailed climate record and a very rich record. Because, for example, here, uh, Ursulor Cave, Bear Cave in Romania, has these incredible bone deposits of past life, of what occurred in that area. If we go into any show cave, they're going to show us their stalactites or stalagmites, all this crystalline beauty. Uh, and yet there's a lot of science and information in these. So, for example, Aven Armand in France has these tall, it's known for its tall totem pole-like stalagmites. And within these is a detailed climate record of temperature, um, gases that, what's the CO2 and other gases in our air during these previous climates. And so we can go into these things and drill them, and trapped within microscopic bubbles within the crystals, we're capturing air that was present thousands, hundreds of thousands of years ago. And we can date the crystal to know the age of these things. We can go into ice in caves, not just in not just in the at the poles and in glaciers, but we can have actually small mini glaciers in caves, and you can see all the banding of sediments, pollen, spores, other material that are there, and again capture detailed records. And there are some really unique records going back to Bracken Cave. I've led a project there for several years, and I'm working on publishing those results now. But my friend here, we're doing some geophysical studies of the bat guano. She's standing on bat guano. And if you're not familiar, put it bluntly, it's bat shit. You know, that's what it is. And it is 30 to 35 meters deep, over 100 feet deep of bat guano. And what we're doing is studying the cave geophysically to understand where we can drill into the cave and take out a core, and there'll be pollen, spores, bones. Remember, the bats eat insects, the various types of insects that were there. You know, there's going to be an incredibly rich and diverse record of past climates, of past environments just in this cave. So the diversity of information is so rich in caves, and that's something that folks are just starting to realize. Now, caves and karsts have a variety of economic resources that are generally not something that most people are aware of. The most common one is oil, and these resources come from something called paleokarst. What this is where you take a karst landscape and over geologic times, millions of years, you shove it deep into the subsurface where different minerals begin to accumulate within those large cavities and voids that occur in karst. And oil is the biggie. It's something we use every day. And so this shows deep deposits of carbonate limestone type rocks around the world, but we're going to focus on the pink ones, which is where carbonate oil is resulting. And so, you know, the rich oil fields of Texas, the Persian Gulf area, the North Sea, rich deposits in Russia, China, Venezuela, Mexico, the Bay of Campeche. These are world-renowned rich oil deposits, and they are also all paleokarst. So not all oil comes out of paleokarst, but certainly the richest, most productive oil deposits do come out of paleokarst. Additionally, there are many other minerals that where the richest deposits come out of paleokarst. Bauxite, which yields aluminum, lead and zinc, copper, phosphates, and over 24 more minerals that are out there. That said, I'm going to go back to one thing, that the most important economic resource that we have from karst is rarely recognized in economic studies, and that's water. Communities don't do well if they don't have water. We can live without all these other things. It may not be comfortable, but we can do without. We can't live without water. And so this is part of my mini campaign to make people recognize that water is a vital economic resource. So caves, karst, and the human spirit. Let's talk about exploration. The longest cave, just to give you a perspective of in terms of cave sizes, the longest cave in the world is Mammoth Cave. It's a bit longer now. It's close to 700 kilometers in length. But when I developed this presentation, it was 676 kilometers of length. I describe caves as the ultimate form of exploration. And the reason is that when you look at a mountain, you can stand at the bottom of the mountain and point to the top and say, there's the goal. You know what the goal is, the top of the mountain. You can point to the moon and say, yeah, I want to go to the moon. I want to go to Mars. You can point to them. You know what the goal is. And certainly climbing to the top of the tallest mountains, going to the moon, to Mars, are not trivial efforts. I've got incredible respect for people who've done these things. But with caves, you don't know what the goal is. Where is the end of the cave? I mean, with Mammoth Cave, it's been explored now since what, the early 1800s, and we're still exploring it. We don't know where the end is. We don't know what's around the next corner. So in that sense, it's true exploration. We don't know whether when we poke our head into a hole, if it's going to take us 5 minutes to explore or 5 lifetimes. So the deepest cave in the world, Veriofkina in Georgia, um, is over 2,000 meters deep, more than a mile deep. This is not that cave, but but actually the upper parts of the cave are pretty small, much like this cave in Texas. And so again, you don't know what you're going to find until you go down it and go into it and check every little crack and crevice and push it as far as you can. As far as size, and people sometimes confuse long and deep with size, but volume is different. The Miao chamber, the Miao room in China, is the largest at 10.6 million cubic meters. Now, this is not that room. This is La Verne in France. It's open to the public. You can go and see this enormous room. And this is about 1/10 the size of the Miao chamber. Okay, so you see there's a little figure here. Okay, you can see some little figures over here. Okay, well, just to tell, and another one over here and over here. Well, actually, these aren't people. This one here is life size. This is just to give you scale, but the ones here, here, and here are basically 2 to 3 times the size of a real human being, just so you can see them. But I'm using this photo just because the cave is lit and it gives you some sense of scale. And again, this room is about 1/10 the volume of the largest. So just to give you a sense of the extremes that we certainly know about in caves. So I'm getting close to wrapping up here. Moving from inner space to outer space. NASA, European Space Agency, and other space agencies around the world are keenly interested in caves. They're studying caves on this planet in order to study caves on other planets. And why? 2 reasons. Habitat, human and non-human. First of all, whether we go to the moon or we go to Mars, and all these photos are cave entrances on Mars. Whether we go to the moon or to Mars, conditions are difficult on the surface. People need to be protected from radiations, micrometeorites, dust storms on Mars, and so forth. Well, we're not going to haul tons of concrete and steel, shoot it up into the sky in the rockets. We'll want to produce those materials locally. So we need a good habitat, a good shelter until we can produce the materials locally. And caves seem to fit the bill. Here's a scale for this one, 100 meters. And so this is almost 400 meters in diameter. This one's 100 meters. This is a little bit more than 100 and something here. So additionally, we're starting to recognize that ice on Mars, but also on the moon, excuse me, occurs down in these things. So we need water. And we can use the water, excuse me, for fuel, hydrogen fuel. On Mars, we currently know of about 1,400 cave entrances. On the moon, we've got about 300 or so, as I recall. So that's one reason. But the other reason is non-human life. Most people feel that it's highly unlikely that we'll find life on the moon, but the possibility exists on Mars, and conditions on the surface are brutal. If life does occur on Mars, it will likely be small. It will likely be in a moist, protected, sheltered environment, which sounds kind of like a cave to me. So there's a lot of research being done in caves, looking at these microbes that I talked about earlier, so we can understand how to recognize microbial life underground and hopefully we can then recognize it if it exists on other bodies up, off of our world. I created this presentation actually toward the tail end of the International Year of Caves and Karst. The year lasted for 2 years because of COVID, but it was organized by the International Union of Speleology to educate basically everyone about the importance of caves and karst and the challenges that they pose. Our theme was explore, understand, protect, because unless you know what you can, unless you explore to know what you have, you can't study it in order to best protect and manage and utilize it. So while the international year is over, I'm currently working on writing a couple of papers, compiling all the information on over 1,200 events and estimated 50 million or more people who have been reached, informed, educated to some degree about caves and karst. And the International Union is now working with UNESCO to create an International Day of Caves and Karst that will continue annually well into the future. Caves are important to all of us. I hope this presentation has helped you see some of that. And so even if you don't live in the karst area, that you are certainly benefiting in some ways from caves and karst. If you want more information about caves and karst, certainly go to the National Cave and Karst Research Institute website. It's been down here in the bottom, ncri.org, ncri.org, and you'll find a lot of information there. You can also go, if you want more technical information, NCRI is a partner with other organizations in the Karst Information Portal, karstportal.org. It's a virtual library. You go there, type in the keyword, and you'll get all sorts of articles, reports, maps, about newsletters, about whatever you're interested in. The International Union of Speleology has a lot of information on their website, and primarily you'll find it under the International Year. Now, this website here is now defunct, but it's been archived on the UIS, the International Year website. So I'll stop here. I'll leave the screen up for a little bit and take any questions. I saw some appeared in the chat. I don't have access, let's see, to the chat right now. Oh, there it is. Okay. Okay. So I see two comments in the chat. One is, what makes the water table? What makes a I should have brought some of the drink, excuse me.
Water.
Yeah, water makes the water table. What happens is that water will move down to the ground and it reaches a point where there's a balance between how deep it can go and where it can discharge from the ground. What goes down, it's got to come up somewhere. So water goes down into the ground, and then eventually it's going to appear at a spring somewhere. And so below the level of that spring, water has no place to discharge. And so the spring can be ultimately, the lowest springs are at sea level and some below sea level. Because during the ice ages, the water table was, sea level was about 100 meters lower. But generally, sea level is the major level where springs occur. But you can also have springs occur at higher elevations because maybe there's a rock layer where the water just can't move through that, and so the spring will come up on a hillside. So it's that balance of where the water can spill out and how deep it can go. If something's not clear, just please let me know. I've told Don and Fred that I'll stay on as long as y'all want me to answer questions. So let me see.
Sure, just want to thank you very much. It was very interesting. So
Had a question.
Brad had raised his hand to ask a question online. We have a couple people in the room that like to ask questions. So if you wants to ask a question, come up and get the microphone.
I'll stop sharing there and
Fred, can you
Yep.
go ahead?
Yeah, thank you, George. Very interesting. Do you do, or has there been any, I guess, geological assessment of caves or the structure before you go climbing into one or go that far under the ground? Do you know what you're dealing with in terms of the stability of the cave?
There's often great concern about caves being dangerous, risky places to go into. There's so many times when I'm asked to do a study, I'm asked to study a cave without going into it. And well, that's kind of hard to do. And I understand the concern because especially Hollywood and loves to dramatize things. You shout and then the roof comes down on you, things like that. If you know what you're doing, and if you follow the rules of safe cave exploration, the most dangerous thing about exploring a cave is driving to get there. And I mean that in all seriousness. That driving stuff scares the hell out of me. I feel perfectly safe underground. Think about it. I was showing photos of, for instance, from Aven Armand, of these tall 20-meter high stalagmites that took hundreds of thousands of years to grow. So that structure's been there, intact, stable for hundreds of thousands of years. So the chances of collapse, are pretty minimal. Has it happened? Yes. Yeah. I'd really love someone to go through the records and compare cave accidents to things like mountain climbing or just simply walking through a national park where you look at a scenic view over a cliff and how many people fell off the cliff or something fell off a cliff down on someone else. Because the rate of injury from things like that, from like collapse or something that happens in the cave, are amazingly small. So that's just part of the training of knowing what you're getting into, knowing what to watch for as you go, so that you don't get in over your head. To know, okay, wait, here's a potential problem, so I need to back out and maybe come back with more specialized equipment. But generally, most of the concerns are up in here. And if you know how to properly manage them, approach them, and again, it's a relatively safe activity. There have been many deaths, there have been many accidents of people in caves, but what I said was when you follow the rules. And most of those accidents have happened from people who are uninformed. Kids, even adults who will go find clothesline and go climb down a hole, that's not proper equipment. Or people, who have pushed the boundaries of safety. And I know I've done it. I'm lucky. I've gotten away with it. But there's some people sometimes who weren't lucky. And so most accidents, injuries, and fatalities have occurred because people were either pushing or ignoring or ignorant of the rules.
Thank you.
Yeah.
We have Heather in the room has a question. Heather?
Yes, hi. I'm finding this quite fascinating. My childhood home in Ohio had a large sinkhole in the backyard, but it probably wasn't great that the septic system was right next to it. What are the options for situations like that can prevent pollution from occurring in those karst areas?
Yeah, good question. I went for my master's degree in Bowling Green, Kentucky. And as soon as I got there, I learned that my advisor had just done a study of a septic system. And it was a state-of-the-art septic system for its time. And everything was done properly, optimal soils, all the fittings, the pipes, everything were done properly. And what he did was, once it was the septic field, the drain field was completed, he went inside the house, he flushed a non-toxic dye down the toilet. And he figured that this dye would be stuck in the soils and clays and for months before it would finally appear in the spring. 9.5 hours later, 1.5 miles away, it shows up at the cave spring. You know, what we've learned is that many technologies that work beautifully in non-karst areas don't work for beans and karst. Now, that's not to say it's hopeless. We are learning. There are improved methods, improved technologies. Now, this was, you know, I went there in 1983, and you know, so this is you know, quite some time ago. If you have an option to have your sewage go into an organized community sewage system where it can go off to a water treatment plant, that's a better option than having a septic system. If you do have a septic system, one of the better options so far right now is to have be on a you know, be in a rural enough area so that whatever effluent does leak past your septic system into the groundwater, that it does not overload the system, the groundwater system at the aquifer. All water has contaminants in it. I mean, if you look at you go into the city records and you'll see what your city water supply chemistry, you know, records are telling you. They'll say, hey, there's this much lead, there's this much arsenic, and so forth. There's minute traces that do not harm us. You don't want to get it above that amount. And so you want to make sure that, you know, in your area, you're not, you're not overdoing it. You're not putting in more than what will naturally filter and biodegrade. You'll want to do a study, excuse me. You'll want to do a study of the system, which way water moves in the area. You may want to do a dye trace. Put dye into that sinkhole and see if it comes out in your well. And so if that happens, and assuming it's just effluent, sewage effluent with no chemicals, you can treat that with chlorine, you can treat it with ultraviolet light. There's ways of dealing with that. And so you may want to beef that up a bit. There was a case in Walkerton, Ontario, where a farmer spread manure, on his fields, and then it rained heavily. The manure got washed down to the aquifer, and it was a perfect storm of bad things because the chlorinator on the well, the community well, failed. And so then they didn't realize it. And so E. coli got into people's water supply. 7 people died. 2,300 people became ill. And the major problem in that case was that they didn't understand the vulnerability of karst. And so having a backup to the chlorinator or an automatic shutdown if it goes wrong, or use, like I say, UV as opposed to just chlorine. What I say is, what I often say as an analogy is, when I get into my truck, it's a useful vehicle, but I already said that driving out there is scary. So I'm going to have that seatbelt on because I know I can get killed. But I want to go the extra mile, and I want that airbag in front of me, and the side bag, and the top bag, and the bottom bag, to protect myself. So go the extra distance to protect yourself, and try to find someone who really has expertise in karst to understand the system. When I started in grad school, there were very few professors who would teach about karst hydrogeology. There are more now in the region. Actually, a friend of mine from Penn State, where I went for my PhD, teaches up at Akron. And Ira's great. So you've got some great people there in Ohio if you still have family and friends back there.
Thank you.
Thanks. Judith, got a question in the room?
Thank you, George. That was a lot of fun. Very cool presentation.
Thank you.
I have 2 questions for you. I'd like to know what the 3 species of cave dwelling beings are that were named for you. And I'd also like to know what the longest time is that you have ever spent underground without surfacing.
The 3 species, one of which is a little spider, Sicurina venii. The genus is Sicurina in Texas, and it's an endangered species. But actually, Sicurina venii no longer exists in the sense that there had been some recent genetic studies, and they found that it was just the, yeah, and I'm not a geneticist, but it was just a few points away from being genetically a completely a different species. And so they decided, no, it's evolving away from Sicurina madula, but it's still close enough to Sicurina madula. So Sicurina venii and madula are considered the same species. So Sicurina madula has taken over Sicurina venii. And which I'm actually pleased about, because I really don't like things named after me. I do it I mention it for the publicity and whatever. But 3 things got named. It's like, guys, no, put a stop to this. The other one is co-named, and it's another endangered species in the San Antonio area, named after me and Joe Ivy, late friend of mine, because we collected it together in this cave. And it's a mold beetle, a tiny little mold beetle called Batricides veniivii. And then the third was something I collected down in Belize. It's a little pseudoscorpion. What was it? Myxobicium venii, down in Belize. So anyway, if you want to make your mark in biology, I mean, it makes it sound special that, oh, George found all these species and he's not even a biologist. It's pretty easy to find new species in caves because people haven't looked there. There's more and more work being done, but there's still a lot still to be done, a lot to be discovered. Longest period of time underground, maybe about 3 weeks. When you go on expeditions underground, it's interesting, because I've watched it with other expeditions and other friends, that before you go in, you're being very careful on the one hand to make sure all your equipment, all your supplies are in order, and that you've got everything you need, and yet on the other hand, you're kind of sitting there soaking up the sun. And I remember coming up, and just sitting back and just taking my shirt off. This was down in Belize, and hot, humid. Took my shirt off, and before I knew it, I was burned because I hadn't had any UV exposure for a while, and it's like, oh, put that drip bag on. But yeah, so it's it's a special privilege to be able to do some of this stuff, and it's something. One of the things that I didn't mention that I should have put this in the presentation. If people are interested in exploring caves, again, this, if you know the right rules, you can do that. You can do it safely. Well, go to caves.org. Real simple, caves.org, the National Speleological Society. I'm a lifetime member, and they are the organization of cave explorers and scientists in the US. They have chapters all around the country. So whether you're looking for a local chapter, if you're looking for something in Ohio and wherever around the country, you'll go there. You'll find on their websites how to find local chapters. They're called grottos, And so there's a grotto here in Carlsbad, New Mexico, of one in San Antonio. There's, I gave a talk for the Boston Grotto, not, during the International Year of, I gave a talk for the group in Columbus, Ohio during the International Year. So there's chapters all over the country. So caves.org, if you want to find out more, know someone who's interested, because whether it takes one trip or a lifetime of trips to get it out of your system, we want you to do it in a way that's safe for you, safe for the people that you're with, but also safe for the cave, where people don't go in and trash out the cave and vandalize it and so forth.
Thank you.
You bet. Thank you.
Roland in the room had a question for you. Roland, take a microphone. Yeah. You're good. That's good.
Hi, this was a fascinating lecture that you've given. I really appreciate you coming. This may be an impossible question, but I was wondering, how deep has water been discovered in the earth? There have been deep wells, and I know the oceans go down a long way. But is there any realm of possibility of, I know the earth is magma inside, and there is a limit, I suppose, as to how far water has been discovered in the depth of it. Do you have any feeling for that?
There's been some recent studies, and I haven't followed them carefully myself. But I've seen some reports and some headlines in some of the journals of water now being recognized, at least through geophysical evidence, and perhaps from some rocks we're seeing, as actually being down in the mantle, not in the sense of underground streams and so forth, but certainly to some degree, there is water down there. As far as water in significant volumes, that's an interesting question. I don't know of anyone who's really set a record or is defined what that record is. I've read about some drilling that's gone down. For example, you can go down into some deep mines that go down a couple thousand, 3,000 meters or more, and water is still produced there. There's a friend of mine did some work in a deep mine in Minnesota, another in some really super deep mines in South Africa. And there's water just dribbling out of the walls. With some amazing microbial communities, unlike anything that we know of on the surface.
It seems like there has to be a limit to how deep it can be found. I mean, I just it's a curious thing.
Well, I think the limit is a matter of volume. So we'll see water in some degree down in the mantle, but in trace amounts. But if you're looking at it as a free flowing stream moving through a fracture, something like that, yeah, that's kind of a moving target. And we're learning more as we drill deeper and dig deeper. But I haven't heard of a limit at this point of what the maximum is.
Thanks. Thank you.
You
You have another
bet.
question in the room? And could you take the microphone and treat it like an ice cream cone? And can you introduce yourself?
Yeah, my name is Harriet, and I wondered, can a person buy a cave? I mean, if I bought a house and it had a cave somewhere on it, would I own it? And are caves regulated like what you do with the cave, like under the EPA or what are they considered, like a natural resource of some kind, or are there limits to what you can do with the cave or what you can extract from it, or can corporations own and make money from a cave?
The answer varies depending on where you're at. In most countries of the world, you own basically the upper meter of the ground, and the government owns what's below. And so when I tell people that here in the United States, we own caves, they say, "What do you mean you own a cave? That's not possible." Well, in their country, it's not possible, but in our country, it is. In our country, it also depends on things like mineral rights. So, for example, I own the house, my house that I'm sitting in right now, but I don't have the mineral rights. So somebody else owns those mineral rights. So if somebody wanted to drill for water, if the oil was found under my house, gold, whatever, someone else would have those mineral rights. I don't own those. And so whether you own the cave or not would depend on if you have those subsurface rights to your property. As far as regulations are concerned, then it also depends. You have like the EPA, you have a federal level of regulation that covers some things, but then you have state regulatory authorities, each of them having their own different set of rules. Some of them will have different rules depending on where you're at. Some states recognize karst aquifers as being highly vulnerable, and they'll be more restrictive in terms of what you can do and can't do around it. Some others don't recognize that, and they're less restrictive. Generally speaking, most show caves are caves that are open for tourism, are owned by the owner, and so they can make money and send people in. There's no problems. The issue of endangered species in caves, there aren't many areas with endangered species in caves, and those are regulated by the U.S. Fish and Wildlife Service. Fish and Wildlife, there's this notion, unfortunately, that Fish and Wildlife wants to take everyone's property away because they have endangered species. And I've never seen that happen, at least not with regard to caves. What they'll do is they come in and they try to work with you. And in most cases, it's been pretty unusual for an owner, let's say just a homeowner like yourself, to not be able to buy a land and have the cave on it with endangered species. Where the difficulty comes in is, let's say you want to build a road and you want to cover up a cave with endangered species, or you're going to build a shopping center and you want to cover up a cave with endangered species. Then what they'll do usually is work with you and say, okay, we'll let you take out this one cave, but for the right to do that, you will then protect these other 3 to 5 caves with the same group of species. So we're trading apples for apples. You will protect those places in perpetuity. And so that's how, for example, highway departments have gotten away with that makes it sound illegal, have managed to cover up some caves with endangered species and so forth, or businesses have done it because they've said, okay, yeah, we'll protect those, and so they develop. If you have archaeological resources, cultural resources in the cave, then again that falls under a different set of regulations. You do have the Antiquities Act of the U.S., but you also have different Antiquities Acts within different states. So some will let you work with them. Federal properties are difficult if you're dealing with human remains because of something called NAGPRA, the Native American Graves Protection and Repatriation Act. There are some tribes who will say, these are the remains of our ancestors. We don't even want you in the cave because you're disturbing their spirits. And so stay out. And so if the cave is federally owned or state owned, they will usually respect that. There are other tribes that are just the opposite, that say, hey, yeah, cool, you found that. Respectfully remove and study them so we can learn from them. And so in those cases, research is possible. But that only affects governmental agencies, not a private landowner. So there's a lot of possibilities in there.
Thank you. I don't see anybody else that has questions or comments. George, I want to thank you for the presentation today. Very interesting. When you were showing the difference between porous media, fractured media, and karst media, it made me think about how do you model transmission of water through a karst formation versus modeling through a sandstone formation
Yeah.
with great difficulty?
Yes, definitely. The models are getting better with advanced computer power. One of the problems we've seen over the years is people will try to apply porous media models to karst, and that simply doesn't work. There's so much stuff I'm trying to squeeze into the program. But for example, there was some great modeling done in San Antonio. Where they're using state-of-the-art modeling. The geology had been mapped in incredible detail. There was over 100 wells in this one area that we were studying. It was about 7 by 7 miles. And the models show that the groundwater is going to go to the east. We put in dye and the water went due south. So some of what's being done with modeling is to use dye tracing data and more detailed geological mapping to help refine these models, but it's incredibly complicated and difficult. So at this point in time, I find that dye tracing is the most effective way of understanding groundwater movement in a karst aquifer. It's empirical data. I put dye in here, it came out there. You don't believe me, I'll do it again. Don't believe me, I'll do it again. Don't believe me, I'll do it again. These are highly complex systems, but we're getting better. I mean, at some point, I think there will be very reliable karst models. Now, I will say that modeling at the broad scale to get a big picture idea of overall where does the water move, how much water is in the system, how it might respond overall to pumping. There's some models that are doing good work in that regard. And right now, what I'm talking about, where we're failing with the models, is with the details. But we're getting there.
Again, thank you very much. It's been very interesting. Presentation.
Glad to do it. Thank you for inviting me.
We appreciate it.